All right, let's get started. Are there any questions about anything? Kind of off the bat. And then I did want to bring up your homework for a second. Let me just get a little screenshot. So I just want to make sure that we know all of the terms from our homework. So specifically looking at this, so it says an ion that is isoelectronic. So isoelectronic means same number of electrons. And so you can have different answers too, right? So what is one example of something that has the same electrons as neutral carbon? So what's, and maybe even, well, how many electrons does carbon have? Right, we can look at our periodic table. So carbon, its atomic number is 6. So what does that tell us about the protons, electrons? What do we say? So yeah, 6, right? So let's, again, don't be shy. So write atomic number 6. So okay, if it's neutral, then we need to have 6 electrons. Okay, so then what's something with 6 electrons? Right, don't think too hard about it. I would look to the left, to the right. how could we change either boron or nitrogen? You know, if you're feeling crazy, you could go to oxygen. But how could you change those such that they would have 6 electrons? So what would we have to do? Oh, Chet is helping you out. So you have nitrogen, and so Chet says nitrogen plus. So if we look at that, right, so okay, neutral nitrogen, we have 7, so 7 protons, 7 electrons, so yes, we could add a plus charge to it. And then, right, you can have fun with it. You could put whatever isotope if you wanted to. 14 nitrogen, you know, this whole part doesn't matter. Or, again, Chet is saving you here. Or we look at boron, right? 5, so 5 electrons, so we could make it boron minus. And I just picked 11 boron for fun. Doesn't really matter. And then, so protons, neutrons, that should be fairly straightforward. And then the term nucleons means the total number of what's in the nucleus, so neutrons plus protons. So that means whatever our answer is has to have basically 12. So what are some answers for E? Well, if we had, so 5 and 7, right, so that's how we add them. But then, okay, so if it's 5, right, that could be boron. So we could, again, pick 12 boron. If we had done 7, right, being neutron deficient, well, that could be nitrogen. So 12 nitrogen. So just as long as it's 12, and, you know, you could really do 12 oxygen, even though that starts to get pretty neutron deficient. But yeah, you can kind of go crazy with this, and there's different answers. All right, so I think that tends to be the confusing part of the homework, just defining isoelectronic and nucleons. But then, of course, if you have other questions, we can go over them. All right, so let's start looking at our electronic structure. And again, I kind of gave y'all a warning that we're going to be kind of dipping into chapter 3, but it's really good to tie everything all together. And so let's kind of take a step back for a second, because again, we may have all different baseline knowledge, and so we kind of want to translate maybe what you've learned in school or whatever to a more refined picture. And so what I mean by that, have y'all heard of the onion model, like the Bohr onion model? So yeah, some people have, some people, and if not, that's okay. And so this is kind of the simplified orbital theory, we'll call it. And, you know, it's often taught in high school, and again, you're kind of given just this overview, and maybe you have this like onion ring, and we have something, okay, well, this is our first energy level, and n equals 2, meaning it holds 2 electrons, and then you go up to your next onion shell, and now it can hold 8. Next onion shell, actually I shouldn't have labeled this as N. Let me put electrons. So N should be 1, so N is 1, 2, 3 for energy levels, and then 2 electrons, 8 electrons, 18, and then I'll stop at 4. So 36 electrons. Does this look somewhat familiar to some people, the onion model? So this is, right, a very simplified understanding. And so, right, we're just, again, kind of treating it like an onion layer. Except, so that's not really accurate. And so now let's kind of look at where we're going, but like I said, we'll kind of break it down one step at a time. And so what we really find, and so kind of how we got to this step here that's in your notes, is this is all from the Schrödinger equation in computational chemistry. I probably misspelled Schrödinger. And so again, right, we don't want to get too much into the weeds of it, but now what we've done, or what computational chemists have done, is, right, they attempt to solve the Schrödinger equation, and then we get kind of this estimation. And so what it's trying to show us is really these onion levels are orbitals, and so we'll kind of look at those. And so just kind of giving you an overview. We have our S ones that do kind of look like the onion shell, but then we'll take, like I said, a more refined understanding and understand that the electrons exist in orbitals that look like this as well, kind of these dumbbells. They exist in these d orbitals where they're occupying, again, these areas. Then we also have f orbitals. But we'll go back and kind of look at this. Okay, so let's start at the top. So literally with hydrogen, because again, we want to see how do they fill, understand that, and then again, we'll tie that to reactivity. And so I like, for this chapter, this P table is pretty helpful, and we can click on the electrons up at the top. And so the next thing that this periodic table now, so if you kind of click right from properties to electrons, you notice it moved helium over, and part of that is just to kind of help group it by, again, these kind of orbital blocks here. And so let's just start there. So this is our S block here, and you may want to highlight this for later, for helpful notes. So again, right, you want to highlight these first two. This is our S block. Okay, and then so some things to note about our s orbital. So all s orbitals only have just one orbital in there, and then they can hold 2 electrons. And so if you look at your periodic table, it's only 2 wide. So that corresponds to, again, our capacity of our s orbital. And so now if we go back to P table for a second. So again, why I like P table is so off on the middle here, it shows us how the electrons fill up. And so of course we selected hydrogen, and then these orbitals are listed in the order of energy. So meaning that 1s is the lowest in energy, and therefore thermodynamically it's going to fill up first. And so again, that's just telling us where our 1 electron of hydrogen is going. So again, it's in the 1s orbital. And so the next thing that we want to do and work towards is our electron configuration. And so now we're starting, so n equals 1. So this is just our first energy level. And again, we want to write our electron configuration for hydrogen. So we have our 1 here to show that it's filling up our first energy level. And then we're filling up the S. And again, what's kind of nice and what you want to correlate it to is its position on the periodic table. So again, right, this is all, so this is going to end up being NS1 is the pattern that we'll get to, but again, we'll see that. Okay, so we're filling up our first energy level in our S orbital, so we know it looks like a sphere. And then, of course, hydrogen just has 1 electron, And so we put 1 electron in there. And again, this is neutral hydrogen that we're talking about right now. So of course, right, if it is plus hydrogen, minus hydrogen, you add or subtract electrons respectively. Okay. So then back to our electron configuration. So this is our electron configuration for hydrogen. So it's just 1s1. All right, so now let's move on to helium. So not too hard so far. So now we can click over to helium. Again, appreciating that now we have 2 electrons in this box here. And so now you can tell from this little depiction that our s orbital, or our 1s, we should say, is full. So let's write that in our electron configuration. So helium, 1s2 now. And so again, kind of note how this tracks with your little onion ring. So write n equals 1 from your onion ring from high school or wherever, and then you're told, okay, it holds only 2 electrons. Now you have a deeper appreciation of why, right? So we have just our first row here, so it was only 2 across. So yes, that's all we did, was we filled up our s orbital. Make sense so far? So ask questions. And so now we go down to our next energy level. And if you wanted, you could kind of write, we have n equals 1 here. Now we'll start our n equals 2, so our second energy level. And so once again, right, we're back to our S block. So now we're filling up lithium. And so we can write the electron configuration. So lithium. So again, we always start from the top, from your lowest energy level. So we start with 1s2. And again, right, it just tracks. So we have to fill hydrogen, we have to fill helium. Now we have to go back to lithium. And so now we're at the second energy level. So now it's 2s1. And right, again, note how it's going to follow this pattern. This is already hinting at the reactivity, like we saw today. So 1s2, 2s1. So there's our electron configuration. And then I'll go ahead and show you the shorthand for electron configuration. So you can always abbreviate it by starting at the previous noble gas. So in this case, it would be helium. And so we could write it helium in brackets here. So that means start with the electron configuration of helium, and then going from there. So then we write helium 2s1. And so obviously right now it doesn't save us too much ink, but as we get further down in the periodic table, you'll probably want to abbreviate it rather than, writing out 1s2, 2s2, blah, every time. And so again, kind of think of what's going on. So this is a lot to think about. And so now that we've dropped to our second energy level, and we can kind of see that, so I'll click, right, there's hydrogen. So we have 1 onion shell. Now we've gone down to lithium. So right, we have like our first orbital. Then there's technically what's called a node, which is an area of no electron density. And then right around it, we start our second energy shell. So again, right, S block, still a sphere shape. And you can kind of see, right, the first energy level is still there, right, just in red, kind of small. And so now let's continue. So we have beryllium. So beryllium, 1s2, 2s2. All right, so now we're at beryllium. And so now let's see what happens when we cross over to boron. And so we're still on the second energy level. And so now let's look at these pictures here. And so now that we're at the second energy level, this is the first energy level where we can have p orbitals. So we have our 3 p orbitals. So they're just formally named for the axes, so x, y, and z. And then, so let's look at our p table now as well. So note there's our p block. So again, we might want to highlight that on our periodic table here. Let's see, so now I'm going to highlight p block. All right, so let's note some things about our p orbitals. So again, if we scroll back down here, well, it told us that there were 3 types of p orbitals. So again, x, y, z, so 1, 2, 3. And then each one of these suborbitals can hold 2 electrons. And so that means we have 6 electrons total in our p orbitals. And if we look at this, how many across is our p block? So 6, so perfect, right? So that makes sense why we can have 6 electrons in our p. All right, good. And so let's just go with that so far. So let's do our boron then, 5 electrons, so boron. So 1s2, 2s2, and again, we're still at our second energy level, so 2p, 1 there. And we don't need to indicate, right, like which p orbital it's in. And then another thing to kind of sanity check yourself, notice that your coefficients should always add up to your total number of electrons in your system. So again, neutral boron in this case, so 2 plus 1, right, 5. Okay, just good sanity check for ourselves. And so let's keep going. So we'll just kind of keep going in order for now. So carbon is 1s2, 2s2, 2p2. And then we'll do nitrogen. So 1s2, 2s2, 2p3 there. And so let's just pause and look at some things about nitrogen. And again, we can point out some things as we kind of go through this. And so notice all these inner electrons. So like going back to beryllium here, like our 1s2 here, all these would be considered our core electrons. And so our core electrons do not participate in bonding. And then right when we're looking at bonding and we're trying to study reactivity, we'd be looking at the outermost ones called our valence electrons. Oh, that didn't help. All right, so then let's kind of look at some other things and kind of how they fill up, because we want to look at some detail. And so now I'm going to write it in a different way. So we have our 2p, and I'm going to write out our 3 orbitals. And then I'm writing out 2s. I'll write out 1s for good measure. So again, right, sometimes we don't show the core electrons. We just kind of drop them. And so nitrogen, 7 total electrons. And so again, note how we fill them up. So we start on our 1s, so we have 2 electrons there. And again, there's only one orbital, so nothing weird about that. Then we put 2 electrons in our 2s. And so then the next question is, well, how do these 3 electrons fill up? And so you may have heard this, again, in like high school or whatever, of the candy rule, right, where everybody has to get a piece of candy first. And so here, we want to have a little bit more refined understanding, because sometimes the distinction that isn't made in high school is that we need to fill up the 2s first. So the 2s gets filled, and then we can fill up our 2p. And so the reason why we have to do the little candy rule and give everyone an electron first is because these orbitals are what we call degenerate. And that means that they have the same energy. And so again, right, the candy rule is nice and cute, but it's not explaining to us what is going on. So what we're saying is energetically, right, all these are the same energy level. And so if we want them to be at the lowest, then it's favorable to put 1 in each one. And the additional reason for that is once we pair it, and I'll move on to oxygen because I don't want to confuse people. So let's compare it with oxygen. So 1s2, 2s2, 2p4 now. And so again, how oxygen is going to fill. So 1, 2, 3, 4, and then 5, 6, 7, so 8. And so once it is paired, the other thing to know is that you kind of pay an energy price to pair. Right, so you have 2 electrons, opposite spins, you kind of have to force them in the same orbital, and so that has a slight energy price. So again, when you're talking about degenerate orbitals, it is more thermodynamically favorable, aka less energy, to put them in the individual orbitals first before you start pairing them. So that's where the candy rule kind of comes from. And so let's look at some other things. So again, we can kind of start to piece together their reactivity trends. And so we can kind of go back to and start filling in. So we said our first row was NS1. Again, right, this 1 indicates kind of 1 valence electron. And then the other thing to think about, and again, this is kind of chapter 3, but it's good to start seeing this, is, well, if they all have this NS1, now we can write their Lewis dot structure. And so I'll just kind of show the pattern here, right? So let's just do group 1. And I'll rewrite the electron configuration. So lithium, we said, was 1s2, 2s1. So again, valence electrons. And so the Lewis dot structure, what it is basically it's trying to translate your valence electrons of your electron configuration to a pretty picture. So what I mean by that is, okay, if we're looking at lithium, again, 1 valence electron, so its Lewis dot structure would be like so. And it doesn't matter where you put the dot. And so, right, we could do the same thing for sodium. So we're getting close to sodiums. And so let's go through the electron configuration. So again, you start at the top, 1s2, 2s2, 2p6, 3s1, right, for sodium. And so again, right, we only want to focus on the valence electron. Now these are the core electrons. And again, right, group 1, this is why they have that same or similar reactivity. And so, right, so sodium, I'll put it on the other side or something different, right? You write it like that. Oops, sorry. Doesn't matter what side. So again, we're just showing, okay, it has one valence electron. And so again, right now, we want to start making the connection on things. So we're kind of seeing, all right, we go down the periodic table here with our NS1. And as we go down, right, we keep adding subsequent onion shells. Now this is also telling us why it gets more reactive as we go down, right? So just think about this morning. So lithium just kind of gently fizzed, right? Sodium lasted longer, kind of ran around. And then potassium was just pretty quick, right, every time I put in the water. And so potassium, right, we're getting down, so N equals 1, N equals 2, N equals 3, N equals 4. So, right, we're getting larger and larger onion shells. That one little electron is then held on more loosely, because remember, your nucleus is still in the center. So as you add onion shells, your electrons, well, valence electrons specifically, get further and further away, thus making it more reactive. So we're already seeing that trend. And so again, I'll just kind of write, so then our generic Lewis dot structure, which is Bm dot for all these kind of group ones. Again, right, one valence electron showing that reactivity. So just thinking about that. All right, so let's see. So let's make sure we're kind of feeling okay. So again, we're just kind of going in order. So we went across, so the 2s, 2p, right, we filled it up with neon, so you can kind of always check your electron configuration on this p table too. Then we went down to sodium. Okay, so let's look at magnesium, and we can also look at the Lewis dot structure. So again, kind of similar thing. As we keep going, we want to recognize our pattern. So, okay, group 2, we'll just start with magnesium because that's where we left off. So the electron configuration, 1s2, 2s2, 2p6, 3s2. And again, maybe we want to practice abbreviating now because this is starting to get a little long. So if we go back to our periodic table, so magnesium is 12. So that means my previous noble gas is 10 here at neon. And so if we want to, we could write it as neon 3s2. Okay. And so again, let's think about the Lewis dot structure. And this is where, again, I want you to take a more refined approach than high school or even other textbooks might say. And so we want to show that they're occupying the same orbital. And so that means that our two dots should be on the same side, like so. So magnesium, right, beryllium, same thing. I don't care which side, just as long as you have two dots on the same side. And that's only because, right, the s orbital is not degenerate, so it's going to fill up first, right, before, if we start putting it on other sides, to me that implies that we're filling up p orbitals, which is not accurate. And so again, Lewis dot structure reflects two valence electrons. We'll see that in the reactivity. So like I mentioned, you'll get to play with a lot of magnesium in lab, so I didn't bring it out for the demo today. All right, so let's kind of see where we're at. Okay, magnesium. And so we probably also want to write some notes here. So maybe 3s, 3p, so you kind of remember. So far it's been straightforward, but it's about to get strange. Okay, so then we can continue. And again, right, think about the pattern. So now we're doing NS2, NP1, right? So 3 valence electrons for this column. And so now we can look at aluminum. Just kind of keep going. So group 3 here. So right, it's called, I think it's 3A sometimes, or 13, depending on your periodic table. And so if we do aluminum's electron configuration, so I'll abbreviate it. So again, starting at neon, and right, again, reference your periodic table for these. So neon, and then have it labeled, okay, 3s2 as we fill that up, and then 3p1. So now we can clearly see, okay, there are my 3 valence electrons for aluminum. And then again, I like to kind of set up this as kind of a reminder of, again, what is our Lewis dot structure going to look like. So 2 electrons in the S, 1 in one of the P's, and so our Lewis dot structure should look like that in theory. I will say you might see it written like so. And so this is kind of strange, but I wouldn't say that this is wrong, because this is, I'll say it's reflective of hybridization. So long story short is these group 3 compounds tend to actually make covalent compounds, which is kind of confusing because they're like formally metals. And you would only know that by examining the crystal structure, and then you would actually see that they make these 3 bonds in this kind of hybridization. But that's kind of an aside for now. All right, so continuing, and so then group 4, so we'll look at silicon. And again, right, we can do our electron configuration. So silicon, again, starting at neon, 3s2, 3p2, so 4 valence electrons. And so group 4, again, we want to write our Lewis dot structure to reflect this. And so kind of, if you're seeing the pattern, the other way to kind of think about this is, right, you have 1, 2, 3, 4 sides. And so, right, you have kind of 4 sides on your Lewis dot structure, 1, 2, 3, 4. Doesn't matter who's who, just fill it up the same. So again, 2 in the S, and then 1 in each of our 2 out of the 3 p orbitals, right? So then we want to show that. So silicon, 2 electrons on one side next to each other, and then the other 2 individually. And this is correct, so this is actually reflective of the reactivity that silicon displays. And now's a good time as any to note that carbon is an exception on group 4. So all the other group 4s look like silicon. So, right, germanium, tin, they all tend to make these divalent species. But carbon's Lewis dot structure, many people write it like this, again, to reflect the hybridization and show that it likes to make 4 bonds. Did you have a question?
I just wanted to know why the silicon, the dots are not like 2 by 2. Instead, like, it's like 2, 1, 1.
Yeah, so again, it's reflective of how they fill up, right? So I want to show that they're in degenerate orbitals, And again, it is actually isolatable as this divalent species, so that is reflective of its true nature. Other questions? So then we'll keep going. So let's just go through. So silicon, so phosphorus is next, and we'll be back at group 5. So again, neon, 3s2, 3p, 3, 5 valence electrons. So again, same thing. Phosphorus has our 3p, 1 electron in each p, 3s, etc. Right? I'm not going to draw the core. So then its Lewis dot structure is like so. You can, where did I put? I think I put nitrogen somewhere else. So nitrogen, just to go back to nitrogen, since I had skipped the Lewis dot structure, right, again, same thing, 2 on one side, 1, 2, 3. So they all have that same structure for group 5 for the Lewis dot structure. So phosphorus, arsenic. So just kind of seeing the power of that. All right, so let's, we might as well just keep going. So let's do sulfur so we can look at all our Lewis dot structures. So sulfur, so now we're at 6 valence electrons. So 3s2, 3p4. Again, right, I would write out our 3p orbitals and fill them up. So 1, 2, and then 1, 2, 3. Then we have to pair one of them. And again, right, our Lewis dot structure should look like that. So we have sulfur. So 1, 2, like so, right? Our S, one of our paired P's, and then 2 lone electrons. And again, all your group 6s are going to look just like this. So I'll draw out oxygen just for completion's sake. What else? I'll just throw in selenium for fun. Right, so they all look like that. Doesn't really matter where the dots go, we're just showing how they look. All right, so then we'll just keep marching through for now. We'll come back and point out some things probably next week, but so chlorine, so neon, 3s2, 3p5. So okay, now we have 7 valence electrons, getting pretty close to our octet. So 1, 2, 3, 4, 5. And so now you're also kind of seeing, I don't know if y'all have heard of the octet rule. We're going to kind of get to that. But now we're seeing where it comes from, right? So looking at the 3p and the 3s, to be completely full, they want 8 electrons. And so that's why we usually have this octet rule. And so again, right, chlorine's getting pretty close to it. This is also starting to hint why the halogens are so reactive, right? Because they're just missing one little electron before they turn into a happy noble gas electron configuration. So yeah, they are ready to react. And then we want to just reflect that in the Lewis dot structure. And so again, all the group 7s are going to look alike. So chlorine, so 1, 2, 3, 4, 5, 6, 7. I probably should have filled it up properly, and then all the rest will look the same, bromine, doesn't matter where the one little electron is, right, like so. And so then let's finish off this row, and things will get a little weird after that, and we may, like I said, we'll probably continue this next week, because we're kind of building upon the two chapters together. And so then, now we're finally at argon, so our noble gas of our third row here. So neon, 3s2, 3p6. And so our electron configuration for our group 8, then you can just fill in with 8 electrons all the way around it to show, yay, it's happy, right? Octet. Again, we're kind of seeing why it's unreactive. Again, we can force stuff. Chemists are always trying to force new reactions, but for the most part, right, inert. Okay, so now let's go back to our electronic structure. So we have just finished off our 3p. However, let's take a pause for a second. So we need to see kind of where we are, especially in our onion ring here. Okay, so we had said we had n equals 1. Well, that corresponded to that. And again, it only had 2. Okay, then we had our n equals 2, so our second energy level. Notice how it has 8 electrons. Okay, well, that is our 2s and our 2p. But then we said, okay, well, we have n equals 3. It should have 18 electrons. But so far, all we've done is our 3s and our 3p here. And so let's answer a few questions. Well, where the heck are those other 10 electrons? And the answer is they're down here. So this is the 3D that starts. And so if you look, right, our third energy level, this is where the D's are first invoked, so they would not show up until the third energy level. And so we have that here. So again, now we have 5 d orbitals. And so just like before, I'll draw it like so, 1, 2, 3, 4, 5, to show our little d orbitals. Each one of these d orbitals can hold 2 electrons. And so there we go, right, 10 electrons total in the d. Okay, so now that explains how we got to 18, right, in this oversimplified model here. And then the only thing that's a little confusing, right, but we just need to follow our periodic table order, and it's also shown here. It's kind of hard to tell, but basically the 4s is lower in energy than the 3d. So we have to fill up the 4s first. So, right, this is our next energy level, so n equals 4. But again, that's why we just want to have it annotated here, right? Because I don't want you to make a mistake, but we have our periodic table, so just label it, right? So we have 4s, so we're at the 4s, so then we'll have to fill it up, right? Potassium will be 4s1, calcium will be 4s2. Then we can start the 3ds. So then we'll fill this up. And then again, right, highlight it. Note how long it is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 across, right, matches with how many d electrons. So that's good. And I'll just kind of label it so we remember that this is our d block here. And then the confusing thing is, and again, that's why I write it on your periodic table. So we'll go in order, then we'll finish up, this will be 3d10, but then you have to remember that gallium, right, starts the 4p. So then we'll go 4p, finish that off, and then we'll pick up with 5s over here. But this is probably a good place to kind of stop. So we're going to keep doing this electron configuration, right? And then we do want to, practice some of these transition metals. So we'll look at a few weird oddities. We'll kind of explain, kind of what I expect from y'all versus where you might see discrepancies and kind of why. And then we'll kind of keep practicing this. And then we'll go over how to fill the rest, because it gets tricky with the lanthanides here too. So we're not done with electron configuration. So we'll keep doing it next week. Again, highlight your periodic table, right? Get it down so far to what we've had. And then, I'm not going to ask for like a super deep understanding of these, but you at least want to know, right? You have an s orbital that's a sphere. You have 3 looking dumbbell p orbitals. You have 5 funky d's, and eventually, right, we'll get to 7 f's. And so at least try to kind of appreciate what they look like. Again, I know this starts to get like pretty advanced pretty quickly, right? Because like what you want to be able to do is in your head start picturing like the s orbitals and p orbitals and all these different orientations, like, and not now, right? Like I'm saying, like in the future, especially if you go on to CHEM and blah blah blah. But this is just trying to lay the foundations. So don't feel overwhelmed either. And again, right, the main thing is, can you do the electron configuration? Can you translate that to a Lewis dot? Kind of trying to understand how this all aligns visually, right? That's going to take time and a lot of working with it. So, all right, so like I said, we'll keep doing electron configuration next week. We'll look at the more difficult scenarios. But for now, so I'll stop lecture, and then you're free to take a break. I'm just going to go ahead and hand out the quiz. And then again, right, you can leave when you're done with the quiz, but try, if you want to stay, work on stuff, ask questions. Recitation is your time. And then I'll leave the stream going in case you had any questions. So just ask questions ASAP before I shut it. And then it is open notes, so you can use, right, all your notes, conversion factors. Just obviously don't ask Google or ChatGPT or anything like that. So no direct searching for answers, but you may use all your resources, all your notes, your textbook. All that is fine. You could use another textbook. And then just turn in the quiz when you're done, and then anything else if you forgot to give homework.
So with the labs, what are you expecting for us to hand it out?
Sorry?
To hand it back the lab report, the lab report that we've done today. When are you expecting it?
Oh, like the lab that we did today? It's
Yeah.
due a week.
Oh, okay. Number 2.
I mean, take your best guess there.
what does this stands for?
You're talking about CC?
Mm-hmm.